Hello, welcome to Advanced Composites. Today is the 5th day of the 10th week of this course. Over the last 4 days we have been discussing about the role played by D16 and D26 as to how they influence the behavior of the plate, and specifically we saw that they influence the distribution of mx within the plate, and also they lead to edge effects, which is the difference between the computed value and the actual value of mx as per the code. So, today we are going to move into a slightly different area, and that relates to the dynamics of these plates, and specifically we will talk about free vibrations in composite plates. Now, when we are talking about the dynamic equilibrium plates, till so far what we had discussed was or we had developed the governing equilibrium equations that was about their static equilibrium. So, the first equation was del nx over del x plus del nxy over del y equals 0. If the plate has to be in, so this was the equilibrium of forces. So, we got this equation from equilibrium forces in the x direction when the plate was in static equilibrium. But if the plate is in dynamic equilibrium, then this right side of the equation, this should be equal to mass times the acceleration of the plate. And if we are talking about acceleration and this is equilibrium in the x direction, then it will be the acceleration in x direction. So, that was second thing, and the second thing is that this is nx is force per unit length. So, essentially what all that means is that this equation gets modified to del nx over del x plus del nxy over del y, and that equals the area density of the plate. Okay. So, rho A. So, rho A is excuse me, yeah, and times the acceleration. So, it is del to u over del t square. So, this is not area density, it is density times the thickness of the plate. Rho, so this is equal to density times thickness of plate. So, this is the equilibrium equation in the x direction. Similarly, the equilibrium equation, so this is for x direction. For y direction, we have a similar equation. Okay. And for the third direction, which is the combination of force and moment equilibrium, we have the following equation. So, I am sorry, this should be del 2 v over del t square. So, all these are mid plane displacements. So, these are the modified equations which have to be considered when we are talking about dynamic equilibrium of the plate. Next, what we will do is we will develop relations for resonance frequencies of these plates, which are rectangular in shape and they are simply supported. So, free vibrations in simply supported plates And here we assume couple of things. So, we assume So, if it is free vibration, then there is no external force acting on the plate. Okay. So, we assume that the laminate is symmetric, which means the B matrix is 0. Second, we assume that D16 is equal to D26 is equal to 0, and the third thing is so here we missed one term, which is minus Q naught or Qxy. So, this is this minus Q, which is a function of xy. Okay. So, going back, we do not have any external forces on the plate. So, what does that mean? So, that means that the plate has, if it vibrates, it will vibrate naturally. It is not vibrating because of some external agent, but it has vibrating in a natural state. These equations also do not include the effect of damping, because if damping was there, then we will also have to account for damping forces in the system. So, that is there, and because of condition 1, because of 1, the out of plane solution and in plane solution these are decoupled. Okay. Out of plane and in plane solutions are decoupled. So, all we have to worry about is the third equation. So, the third equation is del 2 mx over del x square plus 2 del 2 mxy over del x del y plus del 2 my over del y square is equal to rho del 2 w naught over w t square. So, the first thing we do is we want, so our aim is to find w. So, the first thing is we convert this entire equation in terms of w. We know already the expressions for mx, mxy and my, and because d16 and d26 are 0. So, what we get is d11 So, this is the updated equation. Now, to solve this equation, we have, what we will do is we will guess a function, and we will guess it in such a way that it satisfies all the boundary conditions and also all the, and this differential equation it satisfies. So, we guess that w naught xy equals w naught mn sin m pi x over a sin n pi y over b exponent j omega t, where j is equal to square root of -1. Okay. So, this assumed solution has a function of x and a function of time. So, this is a function of x, by capital X I mean space, and this is also a function of time. So, excuse me, this is a function of space and this is a function of time. So, this is the process of variable separable, and now we plug this equation, this relation back into the governing differential equation. So, what we get is this sign terms gets differentiated twice. So, I 4 times. So, I end up with the same sign. So, I get minus d11 m pi over a to the power of 4. So, I will take d11 a negative sign out plus 2 d12 plus 2 d66 m n pi square over ab, this entire thing squared, plus d22 n pi over b whole thing to the power of 4 times w m n sine and m pi x over a sine n pi y over b e to the power of j omega t. So, remember this is omega, this is omega, this is not w, and this equals on the right side rho, and then when I differentiate this term in with respect to time twice, I get j square, and I also get omega square w m n sine m pi x over a sine n pi y over b e j omega t. Okay. So, if you compare the left side and the right side, all these terms are common. So, they get cancelled out. So, if this equation has to be true and then j square becomes negative 1. So, if this equation has to be true, then what I get is omega square is equal to pi over 4. So, I will take pi 4 out, and then I get d11 m over a to the power of 4 plus 2 d12 plus 2 d66 mn over ab whole thing square plus d22 n over b whole thing to the power of 4, and on the other side I get density in the denominator. So, this is my expression for natural frequency. So, omega is equal to 2 pi f n, where, and this omega is again associated with m and n. Okay. So, this value of omega, it varies with m and n. So, this is what I get. Okay. Now, what I say is that let A over B be the aspect ratio of the plate. Okay. A over B. So, I can say that A is equal to B times R. So, if I substitute back this into this equation, I get omega, and what I will do is I will apply a subscript m n, because each natural frequency is associated with this m and n. Okay. So, I just called it the mnth natural angular frequency. So, that equals pi over 4 times rho d11 m4 over b r, okay, to the power of 4 plus 2 d12 plus 2 d66. This is mn over b r square, b square r square, and this is mn whole square plus d22 n by b to the power of 4. So, this is b4 r square, and just to make this clear, this is m, the whole thing. Okay. So, I get omega mn is equal to, if I take the square root of this entire thing and bring out b outside. So, I get pi square over rho r square b square. I take everything b square as well as r square out, then this is what I end up with, d11 m to the power of 4 plus 2 d12 plus 2 d66 m square n square r square plus d22 n to the power of 4 r to the power of 4, the entire thing. So, this is my natural frequency of the system, and so this is the mnth frequency, and this is the angular frequency. I have to calculate the cyclic frequency. I just divide this omega mn by 2 pi, and I will get the frequency, and associated with each of this natural frequency. So, associated with each omega n mn. So, this is the frequency is a mode shape. And what is that mode shape? It is sine m pi x over a sine n pi y over b. Okay. So, what it means is that if the thing is going to vibrate at angular frequency of omega 11, then the shape of the plate will be such that it has one curve in the x direction and another curve in the y direction, and so on and so forth. So, this is the natural frequency of the system, and this we can also call it as 2 pi f m n. So, this is another one. So, this is what I wanted to cover today. Tomorrow we will extend this discussion a little further. We will also see how this behavior of the plates gets applied to isotropic plates, and how do vibrations in isotropic plates as well as in orthotropic plates, how do they differ based on some of the results which we have discussed till so far. So, that concludes our discussion, and let us see what gets extended in context of this discussion in the tomorrow's lecture. Thank you.